In this lecture, we are going to go over an example problem that applies the idea of the radiation reaction. Basically, the force that is dampening the motion of a charged particle due to it emitting radiation. So this is example 11.4. And the idea is that we're going to think of this, this is totally unrealistic, but we'll think of this as a charged particle attached to a spring, and that spring has a natural frequency of omega naught. And then we can apply a driving frequency omega to try and dampen the spring's natural frequency. Okay, so if we start with Newton's second law, then what we have is mass times the acceleration is equal to the force of the spring plus the force of the radiation, which is what we're trying to figure out, plus this driving frequency. Okay. Okay, so let me write this out. So the mass times the acceleration is equal to the spring force, which we can write as minus the mass, the natural frequency squared, times the distance. So that minus m omega naught squared is essentially the spring constant. The radiation is the mass times some constant tau times the derivative of the acceleration. So I'm going to be writing this as a triple integral, and then we have the driving frequency. The driving force. Sorry, the driving force. So this term here, the radiation force, we solved in the previous lecture, where we said it was the derivative of the acceleration, and then there was a number of constants involved. And so we're just going to lump them together into tau, just to kind of make the math look a little cleaner. Okay, so if the system oscillates at the driving frequency, then what our solution should be, the position as a function of time, is some amplitude times the cosine of omega t plus a phase shift. So now if I was to take the derivatives of that, I would get minus omega x naught cosine, the sine of omega t plus delta. And then the second derivative would be minus omega squared x naught cosine omega t plus delta. And then the triple derivative, the third order derivative, would be plus omega squared, omega cubed, x0 sine xt, omega t plus delta. Okay, so if we look at this, what we can say is that the triple derivative is really minus omega squared times the single derivative, or the velocity. So the derivative of the acceleration is just minus omega squared times the velocity. Okay, so that's easy. If we now put that in, what we get is m mass times acceleration is minus m omega naught squared times x plus m tau minus omega squared times the velocity plus the driving force that's applied. Okay, so let gamma equal omega squared times tau, and so what we get is a driving force which is equal to the mass times the acceleration plus the mass times gamma plus m omega naught squared times x. So now what we have is essentially a inhomogeneous second order differential equation with a first order term. And what we can do is we can now take a look at, this is the damping force, that radiation. And so what we can say is that damping force, the thing that's applying essentially friction to slow it down, is minus gamma mass times velocity, or minus gamma m times v. So this damping factor gamma is omega squared times tau, which if you go back and look up and see what that constant tau is, that means that gamma is mu 0 q squared omega squared over 6 pi the mass times the speed of light. Okay, so what have we discovered? Well, we discovered that we can write now our equation for the forces as this second order differential equation, and the inputs now to that are these quantities here, where it depends on the permeability of free space, the strength of the charge, the frequency at which you decide to drive that system, and the mass of the particle. So basically you can put that in and you can figure out how much damping is there going to be, how much of a force is going to be applied because of the radiation that's being produced as it accelerates. Okay, so that's all pretty much all I wanted to say about that. So the next thing is take a look at the next section, section 11.2.3, and we wanted to look a little deeper into the mechanism responsible for the radiation reaction. Because where we left off in the previous lecture is that we said that there is this kind of acausal acceleration, that it seems to me that there is an acceleration applied before the force even gets applied, and that seems rather unphysical. So instead we can kind of think a little bit deeper. Can we come up with a model maybe that would give a better explanation as to why the radiation would be, or what the force would be applied that would slow down the charge. So to think about this a little deeper, it's hard to imagine a point charge as a point. So that gets to be a little bit physically, there's a lot of issues that you have when you have no dimensionality to it. I mean, one can think about it, if this was my point charge, right, and this was my electric field emanating from it, if it's just a static point charge, then just by Coulomb's law, that once you get to this region right here where the electric field attaches to the point, the strength of the electric field asymptotically grows to infinity. So we have this weird occurrence where we have an infinitely strong electric field attached to a single point in space. So instead, what we're going to do is, like I said, come up with a model and say that there is no such thing as a point charge. The point charge is just a very, very small volume of charge. So instead of having a point, what we really want to do is zoom in, and what we have at very small scale, let's say, is a sphere of charge. Then if we have a sphere of charge, we can integrate over it and we can see what some of the forces that are being applied. Unfortunately, solving the case for a sphere of charge and then letting the limit of that charge go, the volume of that charge go down to zero, it has its own mathematical problems. And so instead, let's imagine that this point charge is more like a dumbbell with a positive charge and a negative charge. I'm sorry, two positive charges. If it was positive and negative, they would cancel each other or be neutral. So let's instead say that we have two charges, Q1 and Q2, and those two charges are separated by some distance d. And the case of the point is when we take the limit as d goes to 0. So we can solve the problem, come up with an equation, and then try and take the limit where we let that distance d go to 0 and achieve a point-like status. Okay, so let's set this problem up. Let's just, for the sake of ease, let's have the dumbbell moving in the x direction. Like this. And so the two charges in the dumbbell are moving to the right. And let's say that we now, we started with an x position, x at tr. So that's our initial position. And it's moved now a length L from the initial position in some certain amount of time. And this length here is d. And the distance from where it started up to this charge, I'm going to call script r. Essentially, I'm measuring the position of the charges at some later time. Okay. So just to recap, this is the position in the retarded time. And so, okay. So let's say the charges start at rest and then they accelerate from that initial position. And so we can look at the electric field on Q1. And so the electric field of charge 1 is going to be Q over 2, 4 pi epsilon naught, R over R dot U squared, and then times C squared plus R dot A times U minus R dot U times A. So this is our electric field for a point charge in, with the retarded time. And what I've said was I've made the assumption that I've split the charges evenly into Q over 2. Okay, so I'm going to continue this discussion in the next lecture. So we'll stop right here, and then we'll pick up and see where we can go from with the electric field to the actual force in the radiation reaction.